morning, everyone. Welcome to the distinguished lecture organized by the IEEE student branch of AUT. The talk will focus on real-time situational awareness and decision support for enabling operational resiliency of the DER-rich power grid and associated challenges and opportunities. It is my privilege to introduce our speaker for today, Professor Anurag Srivastava. Professor Srivastava is a Raymond J. Lane Professor and Chairperson of the Computer Science and Electrical Engineering Department at the West Virginia University. He's also an adjunct professor at the Washington State University and a senior scientist at the Pacific Northwest National Lab. He received his PhD degree in electrical engineering from the Illinois Institute of Technology in 2005. His research interest includes data-driven algorithms for power system operation and control, including cyber resiliency analysis. Dr. Srivastava has involved in high-impact research projects resulted in tools installed at the Utility Control Center, supported for more than $60 million by US Department of Energy, National Science Foundation, Siemens Corporate Research, Electric Power Research Institute, Schweitzer Engineering Lab, Power System Engineering Research Center, Office of Naval Research, and several national labs. He is an IEEE Fellow for his contribution to grid resilience and the author of more than 360 technical publications, including 3 books on power system security and resiliency, as well as 3 patents. It's my honor to welcome you to do this. Thank you.
All right, thank you so much. So it's my pleasure to be here, and especially with Raymond, because I worked with him for a long time. But things are changing in the grid, and also with climate change, right? So with weather event, and these are the 2 things that I'm going to focus on today. So first is how many of you have been to control center? All right, a lot of them. Okay, so when you go there, you will see. At least in the US, we see multiple desks, right? And each desk, depending upon its distribution system operation or its transmission system, the role is different. So someone is focusing on security analysis, someone is trying to forecast, like DER and for future, or DER management, or someone is trying to do the scheduling to keep the frequency, right? So power transfer. Each one has a different role, but none of them, all the operators are not trained that how to respond if there is a big hurricane coming, or how to respond if there is a cyber attack on the grid. Right? They're not trained. They go through some drills, which is like, let's say, wildfire. They will do a drill, but they do not know that how to take action because the possibility is so high that if like let's say one weather event comes, it can take different paths, different than predicted, and can damage the different part of the grid. We cannot plan for it, right? So if you know that operator always respond to different events based on what they receive from the power system planning engineers. So planning engineers will do the study, and they will kind of prepare a it used to be a big file, which still is continued. But typically now in the management system, you can put that as a PDF file. And they will open that and say that if this happens, take this action. If this happens, take this action. So that's how they typically do. We cannot prepare that PDF file for extreme events, extreme weather events, right? So they're not trained, but unfortunately, these events are happening more and more, right? So there's wildfire attack, hurricanes, winter storm, and there's an increase in that, right? So if you look at that in terms of climate change, of course, there is a change in terms of temperature. And also, if you look at the number of weather events around the world, there are more and more happening. And that results into the power outage, right? So, and those power outages, it results into alarms. So in the control center, what the power grid operators are seeing is alarms, right? So, and those, if the event happens like these weather event, there will be hundreds of alarms coming at the same time. To know that what to do, they need to prioritize these alarms. They need to look at all of these and then say that this one is more important, so I'm going to respond to that, right? So these kind of events is always puzzling to operators, and there is no tools, existing tools like EMS or DMS, which will help them to take action and minimize the impact on the grid, right? So then the question becomes that what can we do about it, right? So the first thing is we definitely need to give them tools which will look at these alarms and process that and tell them that these are the most important one, right? For that one, we need to detect first. And sometime alarm is only based on the measurement, while we also need to alarm if things are, which is hidden, which cannot be measured, which means that we need to estimate and then generate alarm. We need to classify it. We need to rank it. And then also find the root cause that why it happened. So in this case, it could be simple that there is a weather event going on. That's why we are seeing it. And those root causes also need to be told to the operators with certain confidence. And then decision support and operational tools, of course. Second thing is that we need to train. We need to train the operators, right? Because they do not get training other than some drills for the extreme events. And each event is different. So cyber training will be very different compared to if I train them for wildfire or for another event. And then finally, they need a support team, because even if they come with a control action, which requires a crew member to go and repair it, then without support team, crew member, planning engineers, supervisor, they cannot do that. So with that, let me focus on more on tools today with a limited time. So I'm going to talk about these 4 things next, which is develop tools for situational awareness and decision support. Then validate in control room environment using some test bed, and then also some scenarios which will help them, and then summarize it. So the first one is how do I develop tools which will enhance their situational awareness, know that what's going on, and also decision support. So in this line, we have developed two different tools. One is RPA, which is Resiliency Planning and Investment Analysis. So it is looking ahead. If we know that these are the events that I get hit more often, then how do I prepare for it? And the second one is in operation, RTR mod, which is looking at the resiliency monitoring and operational decision. So when we talk about resilience monitoring, first we need to know that how resilient we are right now, right? And when we say that how resilient we have to always say that, like when we say post-term security, when we say that security against what, right? So you have to say that if it's operational security, then security against N-1, N-2, right, in transmission system. In distribution, we don't have a security concept because it's a mainly radial system, so it does not make sense. But in resilience, when we say resilience, how resilient we have to tell that against what? Against wildfire or against hurricanes. So once we know the event, once we know the system, then we can measure resilience. And for that, we need a metric. Right now, there is no metric which exists as a standard, even though some work is going on for distribution system resilience metric within the IEEE, and then SIGRE. So that metric will, just like a reliability metric we have, resilience metric will also help us to track that we did something and it increases the resiliency metric. And then this next thing comes that how do we define it? So we define the resilience of ability of system to keep supplying critical load. When these event happens, we cannot supply all the loads, right? But if we can supply some, non-critical load, that would be even better. And then we can also use the resilience metric to drive our decision, then take a decision by operator, which is going to enhance the resilience, right? Whether it's a proactive control, or it's a corrective control, or resource coordination. And so that in planning too, right? So now that resilience metric-based monitoring becomes pre-event and post-event. Pre-event means we know that this event is going to come, and resilience concept without any event is not very relevant, right? So we can say that we operate our system in economic mode, in secure mode, and in resilient mode. So the mode is different, right? If there is no event expected that is going to come, then we can keep operating in economic and or maybe secure mode. Once we know that there is an event going to come, then we have a resilience mode, and that is pre-event and post-event, right? So before the event, what we can do? During the event, there will be hardly anything we can do, right? Because it is passing through and we cannot control that event. But the post-event we can do. And then different question that we are asking for decision support is, what I can do to maximize resilience, which is again means maximize the critical load connected and the power that we can supply. We can also ask that there's a battery connected into the system, which is a large scale grid connected battery. How do we charge or discharge pre-event and post-event so that we can use that for supply, right? In planning analysis, also we can do location of switches, location of DERs, also location of automated switches to place so that resilience is maximized. So with all these things in mind, that's what we focused on. So you take the system, which is here distribution system. We also need weather data. We need some spatial information about the grid with DER and all those things. We need some outage history, especially if it has been happened because of event in the past. Then vegetation data, event prediction, and then sensor data. And then we came up with this metric, which we call AWR. A means anticipate, W means withstand, and R means recover. So anticipate metrics, withstand metric, and recover metric. As you can see that these are all for different phases. Anticipate is for ability to anticipate that how my grid will be impacted if this event comes through, right? So event has not there, but it's predicted. Now I'm trying to anticipate that where it's going to impact and what it's going to impact. And the next, we want to know that, is my grid going to withstand it? And if we can withstand that, how much? And that connects to robustness. The next thing is that after the event has passed, how do I recover my load back? So that will tell me the recover metrics. And another way you can say anticipate is event is not here yet. So it's more like a blue sky operation. For withstand, it's a black sky operation because event is here and going on. And recover is event has gone through, and now we are looking at gray sky. So these tools, RPA and RTMAR, is basically designed for different phase. One is for anticipate, and the RPA is for anticipate, and RMAR is for operation. So going further into that, let's first talk about metric, right? So, and then I'll talk about RPA and then RTMAR. So defining resilience, we already did. Even though there are multiple definition in SIGRE and IEEE, and there has been at least 7 different working group, 3 still going on, and unfortunately, I've been part of all of those working group in SIGRE and IEEE. I think that focus should be on critical load because we cannot supply all the loads. And definition is same that we just talked about, the ability of the system to keep supplying power to its critical load. So some of these working group was in IEEE PSDP committee, TND, which is still going on. That is going to result into a standard now. And then PSOP tool for resilience that I chair. And then there's AMPS, which just wrapped up. And then there's SIGRE 4.47 and 2.25. All of these has a very good reports out, if you want to look at. So even FERC has an ability, defines that as ability to withstand and reduce the magnitude. And what we took from that definition, because it was more comprehensive, these three words: anticipate, withstand, and recover, right? So basically, the three words that we took is from FOG definition, and these three also appear in different documents, as we see. So we take that AWR matrix, and first one is anticipate, which is again going to tell me that how well is the system prepared for predicting impact of the incoming event. If you think about that, how well we can predict is it depends on the sensor data. It depends on the historical data. It depends on weather information, and do I have a tool to predict and tell that how it's going to impact, right? So what we did is that we first looked at all the factors which will tell me that how well we can predict the impact. And because these factors, like ability of sensor to predict the weather event, ability of infrastructure model that we have to analyze and predict the impact, these are disconnected factors. So you cannot, it's not like a voltage and current that which is related in the system. And because this is disconnected, we looked at different techniques. And the one technique was CDC, which is Center for Disease and Control in US, is for public health emergency preparedness and response, is weighted sum model. So weighted sum model basically take these factors and give the single matrix out of this. So we applied the same metric which is used by health and to get the anticipate matrix. The next one is withstand matrix. And here, if I define withstand as how well can system continue to supply critical load, what it depends on? It depends on resources, right? It depends on where is my DER, where is my network, right? It depends on where is my critical load, and if there's a path or there is a network that connects my resource to the load. And then it again becomes the network problem, which we can model as a graph theory. It becomes restoration problem in recover, but switching, of course, impacts that. And then I got multiple different factors from the network, from the resources, and from the critical load location. And I can combine that with the multi-criteria decision-making process. In this case, we have used multiple different ones, but AHP was the one that we found to work well. And using that, we define this withstand matrix. And the third becomes recover matrix, which is all about how quickly I can recover from event and continue supplying to critical load. So this is very similar to a restoration problem, but with the resilience-driven restoration, which means that focuses on the critical load and all the things that we can do with the crew member and switching and those thoughts. So with all these three things, now I got my metric, which is a lot of different factors that comes for anticipate, which is combined and integrated with weighted submetrics and give me anticipate metric. We do need a lot of different data. So we need posture model, we need threat model, we need GIS map, some kind of topological metrics, which is coming from the graph theory. And then other static factors, and then also alternative planning strategy if it exists in the already, like sometime distribution grid operator will say that, I'm going to put these many solars, these many batteries in next 5 years. And we can use this resiliency metric to waive that okay, if you do this, if you go on this path, your system will become more resilient. Then on the withstand matrix, we got the critical loads not lost, generation availability, critical load demand, topological resilience, threat factor, and all those things. And these are not the complete list of factors, but very similar to that. And then we combine that with the AHP and then get the withstand matrix. And then from the same thing for gray sky, where we're talking about recover or restoration, that depends on switching operation that we have. A critical load, how many different paths I can reach to the critical load, so that we can close one and then supply the power. And all these things, switching operation, sequence of switching operation, and then again combine with the HP and then give me recovery metric, right? In the grid, resiliency will of course be in economic mode, will be all good. As the event happens, it will go down, and then it will stay there when after the event has passed. It will take some time for planning, and then recover slowly, different set of loads to get back. This can be here, this can be all the way exactly same like before, and different possibility, right? That how well we plan and restore it. Again, in operation, we can do the proactive control and corrective control, which will also minimize the impact on the grid. So the first one is RPA, which helps in planning. So let me talk about a little bit about that. This to more detail is available in one of our website, and actually one utility in Alaska that was a project that funded it is planning to use it. So let's just like any other software, RPA also has a front end and back end, and back end is the one that I was talking about, but front end also is important. So we developed user interface for this. We developed middleware interface for this, and data abstraction layer. So it's all done by students to develop a prototype. And as you can see here, we are using Python, Flask here, SQL, Alchemy, and then a bunch of other software with Java-based visualization. And then we all have a database. And these database is easier because this tool is going to be tied with the existing system, right? So existing operation center. So which means that it can get data from outage management system or DMS or ADMS and get the data over the years in that. It can also look at the SCADA data. If there is a distribution PME data, it can get it. And of course, RTU and sensor, all those things will come here too. Then we need to perform some analysis like a power flow analysis because it's still a steady state. We're not looking at dynamics and transients. We don't need to because goal is impact on the load. And then the threat and impact analysis. So all of these, we can either use the existing ADMS or we can do our own. And then there's a RESTful API and then a user interface, right? So with that in mind, the RT or mod is the next step, which is again looking at the decision support. So there's a lot of things shown here, but what we're looking for is that like these two. If I take some action, then how it will look like resiliency. If I do not take that action, then how it will look like, right? So I can decide between those two. So in decision support, which is RT mod is doing, there are pre-event and then post-event things. And different thing that I want to do for pre-event is like first is damage out estimation, segmentation if I need to do in transmission grid. Also distribution automation, I can do some switching even though it's not needed at that time. So it's like a restoration before event is going to hit. I can form some temporary microgrid anticipating that if the event is going to hit this one of the microgrid, it will be isolated and the disturbance will not spread to other, right? Of course, this is only possible if the microgrid already exists. We can also do some moving generator. That's how typically Army does. They have a lot of access to moving generator for different bases. And then some backup power, we can plan for it. Again, if it exists, then we can put that to different critical facility as needed. For post-event, we can also use mobile generators. We can do the restoration using sensor information, trouble call system, and then the distribution automation and DR coordination. We can also form a microgrid with changing boundary. There are some papers on that. Why changing boundary? Because again, we want to form a smaller system so that the disturbance, if happens here, it will not propagate through the rest of the grid, right? And the other part of this microgrid, if it's not impacted, it can join other microgrid, right? So microgrid with changing boundary will be helpful in that. We can do the network microgrid with some control on that. And then of course, crew is very important because they are helping with final restoration plan. Now I can talk about all of these because we did implemented these in different papers. But let me talk about one, which is distributed control. Why? Because this is more important with a lot of DERs. And during these events, it is not only the power grid, which is all these distribution line is being impacted, but it's also the communication line. And if the network and communication line is impacted, you cannot send the data from, let's say DER to the control center. So in that way, distributed is useful because it does not need the data from location A to all the way to the control center, but you can exchange data among different node, and then it can still solve the optimization problem, right? So of course, we can always resort to local control, which is using the measurement and then taking the control, but it's not optimal. While with the distributed control, which only requires data to be exchanged with the neighbors, still we get the optimal solution. So how does optimal solution work in distributed is you take any optimization function. Let's say you want to maximize the, minimize the deviation from the voltage, from per unit, or you want to keep the frequency to designated value, like 50 Hertz. Sorry. So then you get an objective function defined, and we always have constraints, and which could be quality and inequality. In distributed, we take that and decompose it into each node. Now, of course, the constraint will become lesser, right? There will be only one set of equation there. Control variable will be only for that node and the neighboring node because you're getting the data from there. And once we distribute it, then there are some boundary variable shared between the two different nodes. And we can share that by exchanging the information right here. So n number of nodes will basically exchange now information, and they solve their own optimization. With that, number of iteration is going to increase because none of these nodes has the complete information. They only is talking to the neighbors. So number of iteration, which used to be like, let's say 10 iterations would converge. Now it will be hundreds. But each computation in each iteration, if it was taking like, let's say 0.1 second, now it will be 0.001 second because this is a very simplified set of problems. Very small objective function with only few variables and less number of constraints, right? So in effect, the total time, because what we did with that, we parallelized it. We made this parallel computation. So number of iteration is going to increase, but the total time is not going to change a lot. So with that, we solved the voltage control problem in this, and we saw that the cost becomes, pretty quickly. Pretty quickly means like several hundred iteration, but the total time is very less. So I can talk a lot about distributed optimization. In fact, there is a working group on that, which I chair. And we put out IEEE PS paper out on that distributed optimization and control. It is very interesting if you want to know more about it, different approaches to solve it, and especially very relevant with DERs. So now next thing, it becomes validate in control room environment. And we need a test bed for that. So I had a different test bed, still have access to Washington State test bed and WU test bed and PNL test bed, because I do work at all these three. In the WU, basically we are setting this lab, which is looking at a lot of different tools that we developed at WSU, and this is as part of one project. So Berkeley and Vanderbilt. What's going on here is that we first need visualization. And we have two partner. One is Resilient Grid from Texas, and one is INCSys from Seattle. So these are the two companies with different focus. Resilient Grid is focusing on visualization during the extreme events, while INCSys is more about training to operator during these events. Then we'll have a monitoring application as part of this. And then we have a decision support and control for this. Of course, a database. And then we also have a third company, Ping Thing, which looks at PMU data or distribution PMU data that we are bringing. We have our own tool, which we call Sync AD, which is basically synchrophasor-based anomaly and event detection and classification, which I'm not talking about today, but this tool basically look at the PME data and can tell me the data looks anomalous, or there is some anomaly in that, and then it classifies that why there is anomaly, and then also it can detect the event or reconfirm the event, and then look at log file to to kind of support their classification, and then tell the operator that okay, this is what's going on. Then we also have a cyber part with all this set of data, which we use in case of cyber attack or even to support our weather-based event. So in the system, we did implemented not only existing SCADA-based centralized control, but also distributed control. So this is you can think about these small devices here tied with each DERs, and each of these DERs is getting data from SCADA or from PMU. So this BeagleBone board is representing automation controller tied with the DERs, and these DERs are good in number of sites that it needs control. And then what we did is that we implemented this distributed control that I just talked about with tied with the RTDS and OPLRT, which is actually on this rack, and demonstrated that it can do that. And we on BeagleBone board, we also put this new set of software called REAPS. REAPS is actually designed for distributed control. And we developed working with Vanderbilt University in Nashville, Tennessee, as a part of the two different grants. So all these are mapped here, and the goal is that it works and it controls the voltage at DER very well. Now let me get to the some more scenarios and use cases. So this is specifically for tsunami, which is we worked with Alaska utility, and they asked us to tell our threat against tsunami. So in this case, we wanted to know that crew members and plan assets, and then also resiliency score or resiliency metric chart, so that they can. And this is the basically Alaska system in Cordova, Alaska. And the second thing that we did is operational mode. Again, this is driven by, even though we worked with Salt Lake City, we worked with Idaho Power, we worked with different utilities, but this one is again driven by Alaska system. So we have a system which is, we have network data and all those things. We have some aggregator for database. Then there is ADMS, and this is where we put our MOD. There's also a crew logistics. This was a little bit different that they had some automated switch, and then they had some switches, which is more like a manual, and that requires crew to go and change it, right? Open or close. When that happens and we want to reconfigure a system, of course, we cannot reconfigure till the event has passed, but we can reconfigure the system in a proactive manner, which means that even before the event is going to hit, which means that I need to keep the crew safe and still do the switching operation even before the event is going to hit to minimize the impact. And then it becomes optimization problem to solve. So this is proactive restoration even before the event is happened, but it will minimize the impact on the system. We do need some data. So we need to know that if the event is going to come, then what kind of lines and generators it is going to impact and get those out of the system. So that prediction need to be right. And then also switches which are available is some are manual and some are remotely operated. And that's why we need to do in 2 steps. Sometime our forecasting may not be correct. So there's some probabilistic based analysis here too. And then it becomes 2 stages, one to operate the manual switches. And then the second stage, we operate the remotely operated switches, because I can do that like 30 seconds before the event is going to hit. Oh, so this is how Alaska Cordova system looks. They have a hydro, they have a diesel, and pump hydro, and small town. It's basically a fishing town. And then of course we also applied the same logic to IEEE 123 bus system because we wanted to publish it. But Cordova system, we reduce it to a smaller system, to 45 node system. So this is how it looks like, with some set of generators here, then some set of generators here, and then some set of generators here, right? So they have hydros at 2 locations. And this is a reduced network, and then some bunch of diesel, and then they also have a battery. So with these 2 systems, let's say the tsunami is going to hit, and then we find that this black region is typically historically will become flooded, which means that you will get you will lose those that section of the system. You will also lose the section of this generators when the flood happens. And 123 bus system, we did some hypothetical, just based on that where the event is going to hit and what it will impact, definitely, which is a darker gray, and the lighter gray represents that will probably impact. So now it becomes that you got some event data, and then you have a distribution system, and then we have a early warning in place, which will tell me that this is going to be impacted. And then I got this, renewable generation or DER forecasting. I got my load forecasting, and all these things together with logistic and crew approach is being coordinated for this 2-stage operation. So there's a lot going on. I don't want to go in detail of this, but basically what it is doing is that like we discussed before, that there's economic mode and then there is a resilient mode, right? So in economic mode, we have forecasted the event, which is right here. And then if it is if it's forecasted and saying that, so it will be only trigger if there is a high impact, low frequency event forecasted. And then we are talking with our ADMS or DMS or OMS, all of these things. So one thing is that we calculate the resource requirement for different DER. It could be battery, right? Which need to be done proactively, right? Because you definitely want your battery to be fully charged before the event hits. And then we have a map which rates the weather superimposed with a GIS map of the power grid. So we can exactly see that what will be impacted. Then we get the resiliency metric here calculated. And then, we look at all the load generation, renewable generation available and forecasting. All these data feeds to our engine, and it is being done in the 2 steps, right? So in step 1, we are doing proactive decision support, which is basically switching manual, because we cannot do that, just before few seconds before. So we need to send the crew at least 30 minutes before or 45 minutes before the event is going to hit, so they can come back safer. So this is the proactive decision support, which is switching the operation, line flow and generator set point decision in stage 1. And then the second part, so we get that this is same thing, stage 1. Then step 2, we are doing the proactive, safety constraint switching. And this we can do again, because this is automated one. So we can do that 30 seconds before. And then all of these will basically result into the switching configuration, DR output, and then the load being supplied with all the map. So all these things can be formulated, and that's what we did with the 2-stage proactive control, with considering all the distribution system, radiality, all the healthy subsystem, including macrogrids, local generator capability, DER capability, nodal flow constraint, line flow constraint, power flow constraint, and the voltage limit constraint. And then also, looking at healthy part and the part that being impacted. Then also limit switching operation. And then we had constraint for stage 1 and stage 2. So some more results here, it clearly shows that if the event strike, which is the red one, as soon as it happens, the resiliency will become very less, right? Which is expected. If I don't do anything, the resiliency will become very less. If I do take some action, right, which is 2 different things. One is proactively, and then the second one is through also remote switches. And as you see here, in the second case, if I take this proactively, the blue case, resiliency is highest. And this green one is not visible, but it's actually right here below this. So which means that if I do proactively, my resiliency might go down a little bit in the start, which is okay, not a big difference, but later it becomes much higher. So another work that we are doing is, and there's a lot going on here, is basically that the tool that I was talking about, Sync AED. So it looks at the events and the damage part, then detect those, then look, then do the alarm generation, then do the classification, then do the what kind of event it is and the root cause, and rank them, and then basically help decision support. So I'm not talking about this part, but in terms of decision support, think about a problem that wildfire is basically moving through, maybe let's say 3 different locations in the system, which is actually common, like in California, Washington, and Oregon, and even Alaska. Wildfire happens often. now I have to decide that what proactive action I can take to minimize the impact against the wildfire. And then you realize that this optimization problem becomes, very challenging to solve. With RL, reinforcement learning, we can, if it's trained properly, we can get the solution in a better way, and we can embed the physics set of equation in RL in multiple different ways. First, it's trained on the power flow based solution, so
Yes.
space will not be out. And then, with all these things, there's a lot going on here too. That first thing is RL is trained, so this part with a simulated power system operation. And the second one is that
Well,
once we get the RL solution, we apply some set of power flow feasibility to check that the solution is feasible or not before implementing it. So that part is right here, real-time system operation. And we also developed this, digital assistant for grid operator, which is NLP based, because during this operation, operator is stressed and they're looking for some information. Instead of trying to find themselves, they can simply ask this text question, right? Which is, this is NLP based, and now we are working on large language model too, and which we call it Dingo. There's a paper on this too. So I did talk about a lot of different things, but essentially, as the event is increasing, all of these event is increasing, we have to think differently because existing EMS, DMS is not designed to handle these extreme events. So which means that we need to put new tools in front of operators, which will still leverage all the data set, all the analysis that we already have in DMS, AMS, and also with the possibility to do the restoration while keeping DER in mind. Because now we can, especially if DER is grid farming, we can even make a smaller system with grid farming taking the lead, even without macrogrid, if you have a controller, right? So we can make an island with grid farming inverters and controller to operate as a macrogrid without macrogrid controller, right? So all these possibility exist, and possibility typically means more number of control variables with more flexibility, which becomes more difficult to solve. A lot of these problems becomes large scale optimization if you want to solve centralized, and then sometime ML like RL I talked about helps to solve those optimization and make a decision. We should always keep in mind that we embed the physics equations in ML, so we get the feasible solution. And then validation is very important for these, and we can only do that in simulated power system, not in real grid, because these events does not happen often. The other thing is that operators are typically stressed during these because they have to move very quickly during these events. And in one of the projects, we are looking at a term called cognitive flexibility. So just like us, we also have cognitive flexibility, memory, and different things, right? If we have more cognitive flexibility, an operator has more cognitive flexibility, they can make a better decision for something which they are not trained for, right? So there's a correlation between cognitive flexibility and making decision for something that they are not trained for. And you can actually measure it. There are psychological tests, which I'm working with my collaborators and bringing operators in our lab, and we do this test. We also have the stress test, which can see that how stressed they are, because our tool should be designed in such a way that they become less stressful because they have access to data. And this is called a skin response. So there's a small device that we put that on their finger while they're thinking through this simulated hurricane case or simulated tsunami case. and they can decide, make a decision to minimize impact, and I can know exactly that how stressed they were when they were making a decision. And we have other things too. So we are working with this cognitive performance and dynamical attention control framework to analyze the human aspect. With that, thanks once again, and I'll be happy to take some questions. Yes.
So my name is Kelvin, and I'm doing my PhD in smart grid cybersecurity at University of Auckland. I'm also working as a network planning engineer for Vector. And it's good to see you again after the Australian conference. So I've got a quick question on, I've got few questions. So one is regarding the distributed optimal control. So you mentioned about each node will have like local objectives and local constraints. So is those constraints can be thought of as dynamic operating envelopes or?
Yes, you can design in such a way. And yeah, so I did not talk about distributed control, but this is challenging problem, especially that how I can solve in minimum number of iteration, because that's one thing, right? You can have a dynamic envelope on that, and you can, like frequency one, actually we solve with Auckland University in Germany and MIT. So they were the collaborator in our project. They solved the frequency one with the dynamic envelope while we focused on voltage control.
Thank you. And my second question is regarding the threat models for the AWR metrics. So is it integrated from a different source, or how does it work?
Yeah, so threat model will be basically based on the community that we are working with. So for example, if you work with Alaska, then they will tell us that, they want to analyze snow avalanche and they want to analyze tsunami. So these are the two things that we model. And the reason was that because we had access to historical data, that how many times it happened. Sometimes it happens like once in 5 years or once in 3 years, but snow launch was happening more often. And they had data which will tell us that, this hydro plant will be basically blocked because of a lot of tree falling into reservoir. So we did model that. We need some background from the expert, which is there. Yeah.
And my last question is regarding the RPIA tool. So as we are working in the distribution company. So is it something as a product that you can offer to the distribution companies? And then you also mentioned we can do the power flow analysis. So does it have the capability to integrate to our, like, let's say, DigiSilent Power Factory or?
It does, yes. Yeah, so it's a design and then already being used by different operators. It's not a product, it's a prototype. So which means that there has to be some work done by the utility to take this and then work together to, to start making the production stage. Yeah.
Thank you.
Hi, my name is Zainab. I'm from University of Auckland. So my question was with regards to information security threat, cyber threat. In that case, in the case of physical threats, tsunamis, whatsoever, we can predict we have historical data to predict what sectors will be affected and make corrective actions. In case of cyber threats, how we cannot predict, I might be wrong in this, but how would we predict which sectors would be affected and how would you simulate that? Is there historical data about it?
Yeah, so even if there is historical data, it will be very challenging to, think that it will happen in the same way, right? Yeah. So in cyber attack, it's very different, and you focus on operation more. which means that we have to rely on detection. And not much can be done unless we detect it, that there's someone in the system. Now, detection is based on the cyber data, right? So, which I did not talk about that because we have a different set of tools to detect from the cyber data. And once we detect that, then you can be proactive before the attacker is in another set of systems, right? So if the attacker is here, compromise 3 devices, they will get into the next one, which is connected to this device, right? And if we detect it here and we know that this is not compromised, then you become proactive, right? How do you isolate this so that the rest of the system is safe?
Oh, no, yeah. Are there any questions from the audience online? It seems like there are no questions from the online audience. So I'd like to thank Professor Srivastava again. And then I'd like to invite Dr. Raymond Zamora for the closing remarks.
Thank you, Vinay. Thank you very much. Thank you very much, Professor Srivastava, for the very interesting talk today, and also to come very far away to New Zealand. And yeah, and thanks all the audiences, like in person or online, for the coming to this distinguished lecture today. And also special thanks to our Industry Application Society chapter, New Zealand North Section, and represented by Professor Patrick Hu here for sponsoring this event. And of course, thanks to the organizer, especially our students here. Special thanks to Upini, Alpi, and Babar, and also some other people who I might have not known that they have contributed to all the preparation to the event. Yeah. And of course, it is a long journey for Professor Srivastava to come here. And before coming here, he had also distinguished lecture in India, and also had some keynote session chair and paper presentation at ETFG Wollongong. Actually, we met in Wollongong after so many years, right? I left him in 2016 after my postdoc. I started when he was in Mississippi, and then he moved to Western State. I followed him to Western State, and then in 2016, I moved to New Zealand. Basically, we met just Monday, right? Monday we met, like the first day of the conference. We met last Monday after so many years. And I know that Professor Srivastava is very hardworking, but we know that, from the voice, we know that, it is tiring trip for him. So, yeah, of course, we can learn a lot from his distinguished lecture today. And for you who still have some question, we will have lunch after this, and then we can still discuss a little bit. casually. And then, of course, I mean, if you still want, we will, I mean, like, you can email him as further question. And we will share this recorded video and also presentation. We will ask permission from Professor Srivastava first, okay? And that's all from me. Before we close, I would like to ask Patrick to give a token of appreciation to Professor Srivastava. Don't worry, Patrick. We prepare it. Yeah. Picture.
Yeah, great. Yeah.
Thank you.
Thank you.
Thank you. Yeah, we can have lunch. Okay. Thank you very much, everyone.